This is a lesson in University Physics, calc-based physics on capacitor networks. In a prior lesson, I had talked about capacitors in general, the physical parameters of a capacitor, how charge can be stored on a capacitor, and also how because charge is held a distance apart, there's some potential energy stored in that electric field between those charges, and we can quantify that with the energy of a capacitor. So those are all prior lessons that I had recorded. I wanted to remind us of how charge gets stored on a capacitor when I hook it up to a battery. I have a 12 volt here, and this is just from the prior lesson that I had recorded. The battery is how we think of it is we model conventional current, which is the flow of positive charge. So positive charge gets pushed from the positive plate to the battery to one of the capacitor plates. That'll be the positive plate of the capacitor. Because there is a net charge of 0, the corresponding negative charge will be left on the negative plate of the capacitor. And so when we look at this equation, Q equals CV, that is the charge, that Q is the charge on the positive plate and the charge on the negative plate. The value of those, they'll be equal to each other in magnitude and opposite in sign, and that's that Q. There's not a factor of 2Q in there, so don't worry about any of that. So what we're going to do is, to make this more complicated, is we're going to put more than one capacitor into a network. And so we're going to be looking at series capacitors and parallel capacitors. We're combining elements into an equivalent. And we had done this in a prior lesson with resistors. This is very similar if you have mastered some of those requisite skills for resistor networks. You're going to see some of the same skills come up in the capacitor networks. So series, we're going to notice that circuit elements share the same branch. So you see this circuit on the left. Those two capacitors are in the same branch as the battery, right? If I follow that branch, if I follow that wire, once I leave one of those capacitors, I have no choice but to go through the other capacitor and go back to the battery. As opposed to parallel, where I leave the battery and then I have this choice of going from one to the other. So that's how I tell two things are in parallel with one another, is if I have a choice, if two branches are in parallel with one another. We're going to see an example here in a little bit that it's just not as easy as like it's in series or is in parallel, because we can have more complicated circuits going on. But that's how I can tell if two branches are in parallel, is if there's a choice to go down one or the other. Both of these branches have only one capacitor, so we're going to say those capacitors are in parallel. To quantify those numbers, right, once we are identifying whether they're in series and parallel, we can do some calculations. Series capacitor adds like a parallel resistor. Okay, so we're going to have a 1/over relationship here. Watch out for your algebra on these when you're adding. And I can do more than two capacitors in here, right? I can have C1, C2, 1/C3 plus 1/C4, and so forth, just to encapsulate all of the circuit I'm looking at. Once we simplify down these two capacitors into their equivalent capacitance, I'm going to redraw the circuit. There's the battery. So that I can see that the voltage across this equivalent capacitor is equal to the voltage across the battery. It's simple in this situation. But what happens is this V1 across this capacitor and this V2 across this capacitor add together, right? When I simplify them down, because they're in series, following like Kirchhoff's loop equation, when two things are in series, their voltages add together to equal an equivalent one. So I'm going to keep that relationship in mind. Another relationship I'm going to give you that you'll be using when you solve capacitor network problems is that the equivalent charge, so when I look at the equivalent charge on this equivalent capacitor, Q equivalent, all right, it will be equal to the Q1 on the capacitor 1 and equal to Q2. And I know you want to make it like the voltage equation, like it would seem like it's intuitively that like that. But let me explain to you a little bit why they're equal. This is how I remember in series they're equal. Is that remember, this battery is going to push positive charge this way onto this plate. Let's say I have two, whatever's stored there. Well, what happened was the battery pulled those two charges from this plate over on this other side with C2, and it will have a -2 on that side. Remember, Q net for the whole circuit is 0. So if I have 2 over here, there has to be 2 over there. Well, if there's 2 negatives there, then there must be 2 positives here. And if there's 2 positives there, there has to be 2 negatives here. And so we're seeing that all of those charges, Q1 and Q2, are equal to one another. And when I simplify it down, it'll be the same thing on the equivalent capacitor. This is a nice relationship if you're trying to find charges on you can find charge on the equivalent capacitor, and then you can distribute that charge in different ways across a different circuit to figure out what charge is on the other capacitors. So those are some nice relationships for the series. Let's look at parallel. Parallel, we're going to see that the equivalent capacitance for a parallel circuit looks like resistors in series. Okay, so they just add together. And when I redraw this, what I think of this as is I'm just taking this whole capacitor, these two plates, and just kind of connecting them together. Do you see that? So I just have this Q equivalent or the C equivalent here, and I'm going to hook it up to the battery. And so that's my equivalent circuit. What we're going to know is, because we know any two circuit elements that are in parallel, we can see these two are in parallel with the battery. Because they're in parallel with the battery, because they're in parallel, they're going to have the same voltage. Okay. So the voltage across here, V2, is going to be equal to the voltage across here, V1, which is going to be equal to the V equivalent for those two capacitors. Okay. And then in this situation, the charge adds. Remember what I was saying about, I think of these two capacitor plates just connecting together. Well, the charge on this plate will just add with the charge on the other plate. And so that's how we get this relationship, Q equivalent equals Q1 plus Q2. I'm going to give you a summary slide for all this stuff, but what I wanted to do is step a little bit into strategy, some tips for combining series and parallel capacitors, all right? So when you're doing this, notice what I did on the other two circuits was I had redrawn the circuit. And I know that you all want to do this in your head. You have your short-term working memory, and you want to just keep that stuff in your head. Draw it out on the paper and keep all that stuff organized on your paper when you're redrawing circuits. And you can do this as many times as you need as you're redrawing circuits, or you have equivalents. You can look at different combinations of that circuit so that you can identify different voltages, different charges, etc. Okay. Remember, with series, there's no choice along a path or a loop for two circuit elements to be in series, and in parallel, there is a choice. So when you're redrawing, that should help you draw out the circuit. Once you get things redrawn and you're looking at relationships, notice that you can use the relationships for voltage and charge for series and parallel, along with this relationship that we learned previously in capacitors, Q equals CV. And you can relate charges and voltages with that Q equals CV, and also with whether you're in series or parallel. So I'll give you an example of that. What I did, I know these equations aren't too complicated, and you've done resistor circuits before, complex resistor networks. So I know you're wanting to jump into just a complex capacitor network. Let's do this real quick. Part A. I think we can do part A real quick and get an idea of what's going on. Part B and C and D aren't going to be as easy, but we'll just start with part A. What I have is a capacitor network, and you can see that we start at A, and there's a whole series of capacitors, and we end at B. They give us the values of all those capacitors. What is the capacitance of the circuit between points A and B? And there's a lot of stuff going on here, right? I think you can't just do like an easy plug and chug on this. What I'm going to recommend is that you redraw this circuit so that it's recognizable. What things are in series, what things are in parallel, right? C2 is in the middle here. It's not really in series or parallel with anything else. So how do you add that in? So let's redraw this circuit. And I'm going to start at point A, and I'm just going to go up and down. For me, going up and down is an easy way to look at a circuit. So if I start at A and I follow the wire along A, I get to C1. So I'm just going to draw C1 in here. There's C1. Okay. Once I leave C1, I get to a junction. All right. So I'm going to draw C1 and I'm going to draw a junction. When I get to this junction, I can go to C2 or I can go to C4. So I'm going to do that. I'm going to put C4 over on this side, and then I'm going to put C2 over on this side. Okay. Once I go through C4, I'm going to go back to B, which is interesting. I'm going to hold on to that side of the circuit. I'm going to keep doing this more complicated side, and when I get done drawing it, I'll connect everything. All right. Once I go through C2, I get to another junction. So I'm going to, on this branch with C2, I'm going to put another junction in here. From this junction, I can go to C5. So I'll put C5 there. And over on the other side, I can go to C3. There's C3. Once I go through C3, I have no choice. Remember when we're looking at choices, if I have no choice, they're in series. So C3 and then C6 goes here. Once I go through C6, I'm at the end of C5. So what I'm going to do is I'm going to connect the end of C5 and the end of C6. Once I get to this junction, I see that I connect back up with C4. So I'm going to bring this branch all the way down from C4 and connect that. And then that's the end of my circuit, B. Okay, so now that I have that drawn, now I've redrawn the circuit, right? So always redraw so it's something recognizable. Hopefully you're seeing the little parts of the circuit in here that you need to add together. I can't do anything big with the circuit till I start condensing things inside. And the smallest part I can start condensing inside, can you guess where it is C3 and C6 get added together, and they are in series. Okay. Once you add those in series, it seems like then you can add, I'm going to call that C36 because it's C3 and C6 added together. Then I'm going to add C5 and C36, and you're going to see that equivalent capacitor, those two capacitors are in parallel. So I'll call that a parallel. Okay. Once I get those added in parallel, let's pick another color. And let me simplify this a little bit. Maybe if I redraw it, I'm going to still have the C1 on top. I haven't done anything with that. I'm going to still have the C4 over there. I'm going to have C2. And then at this point, after the green and the blue simplification, I'm going to have this capacitor I'm going to call C356 because it's 3 and 5 and 6 combined together. Okay. So hopefully you're seeing, when you redraw, all this becomes a little bit more visible to you to be able to simplify. I can't do anything with C4 until I simplify C2 and C3. Oh, I picked a different color. Come on. There we go. I'm putting it in pink here. These two are in series with one another. Once I get those two in series, I'm going to add it in parallel with C4. So there's a parallel. And then our last step, notice that our last step, we'll call this, I'm not going to call it anything. So we go from there to there to there. Let's draw the final. Once I get those two in parallel, I'm going to have C1 in series with, what is that? The rest of them, 2, 3, 4, 5, 6, right? A, B, this is C, 2, 3, 4, 5, 6. And that will be our last simplification there. Okay. So let's go through and do this. Let me get my green marker back out. We're going to add C3, 6 is going to be two of them in series. We know that they add in 1 over in series for capacitors. So C3, where's C3? C3 is 22.5. 22.5, and then I'm going to add on C6, which is 1 over 51. Remember, we have to invert this. Once we add the 1 over and 1 over, we have to invert it, and then that will equal a nice 15.612, and this is microfarads. Okay. I'm going to keep going on this. Let's add the blue portion here. The blue portion, we're going to call this C356, the equivalent capacitor. These are in parallel, so we're going to add them together. I'm going to take C5. C5 is 77. And then I'm going to add it on to C36, which I just found, 15.612, and you can do that in your head, maybe 92.612 microfarads. Okay, I'm going to move on to the pink loop, or the pink simplification here. Now that we have those added together, C2 and C356 are in series with one another. Let's do another series. C2 3, 5, 6 equals 1 over C2, 39, plus 1 over that equivalent capacitor, C356, which we just found, 92.612. Don't forget to invert that term. All right, and when we run that through the calculator, it's going to be less than both of these numbers because we're adding 1 over. It's going to get smaller, so we have a 27.443 microfarads. We're going to do the purple simplification with the parallel here. C4 is in parallel with C2, 3, 4, 5, 6. C4 is in parallel with C2, 3, 5, 6. Okay, so we'll do another parallel. C2, 3, 4, 5, 6 equals C4, 30.5 plus 27.443 is a 57.943 microfarads. Okay, one more step. We'll do our one more step over here if we want to find QC equivalent, which is all of them added together. 1, 2, 3, 4, 5, 6. We have a series. We're going to have to do 1 over C1 plus 1 over C2, 3, 4, 5, 6. So we'll do 1 over C1 is 49 plus 1 over this number we just found, 57.943. And don't forget to invert it. When we run this through your calculator, you should get 26.5489 microfarads. That is the equivalent capacitance between point A and B. All right. So I can model A to B as this C equivalent, A to B. Okay. So that's kind of fun. If you've done resistor networks, it's very similar except the equations are switched. You just simplify each little part as you go through. Okay. So kind of fun. Now that we have the equivalent capacitance, 26.5489, a bunch of good numbers, 26.5489 microfarads. There's more questions here. It says a 3-volt battery is connected to points A and B. So put a battery in here between point A and B. There's the voltage across the battery. But what we're going to do is take a pause for a second, do a couple of simpler networks, and come back to this more complicated one so that we'll look at simple ones and have some tools to look at a more complicated one. What I'm going to show you, and you may want to screenshot or put this in your notes, is this summary slide about how things add in series and in parallel for capacitor networks. Okay, there's a sketch, there's the equation, the voltage. Notice the voltage equations are not the same and the charge equations are not the same. So you can come back to this information and reference it when you're working on problems and need a reminder. I'm going to remind you again to redraw your circuits. We're going to continue to redraw circuits as we move to RC circuits. We're going to move to LC circuits. We're going to move to RLC circuits. All of those are going to need redrawing because they're time dependent. Just get used to redrawing circuits for yourself, and that will help with solving your problems. I picked a simple series network to work on first here, just for practice, to remind us of the basics of charge and voltage when we're looking at different capacitors in a circuit, right? What's the equivalent capacitance? Well, I can do equivalent capacitance here. That isn't going to be too bad. So part A, I'm going to take Q equivalent is 1 over C1 plus 1 over C2. And I can do that real quick. Don't forget to invert it. So I'm going to go 1 over 16.5 plus 1 over 49.5 and invert it, and that will give me 12.375 microfarads. So that's part A. We got part A done. What's the equivalent capacitance? Pretty easy, right? What's the charge on each capacitor? Well, remember what I was saying earlier. When I have capacitors in series, their charge is going to be equal to the equivalent charge. So when I redraw this circuit, remember I was just telling you about redrawing circuits, I have a C equivalent and it has a Q equivalent on it. And when I look at this Q equivalent, I'm just going to relate it to the voltage of this battery. Q equals CV, right? So if I want the equivalent charge, I'll use the equivalent capacitance and multiply it by the voltage that capacitor is getting, which is from the battery here. Okay, so I'm going to note that Q equivalent will equal C equivalent, 12.375 times the voltage on that battery. It's a 21 voltage battery. 21 volts battery. So Q equivalent is going to be 12 times 21, yeah, that's over 200, 259.875. And I'm going to keep this in microcoulombs. Okay, so that's Q equivalent. I know that Q1 is also going to equal that, and Q2 is also going to equal that because of this relationship here. What's the charge on each capacitor? Done. What is the drop of potential across each capacitor? So what they're looking for is V1 and V2. What is V1 and V2? Well, when I'm looking over here, V equivalent equals V1 plus V2. I don't know either of those values right now. I know they must equal 21 when I add them together, but I don't know each one individually, so this equation actually isn't helping me right now. What will help me is I'm going to recall that Q equals CV, and note that we have Q for each one of these capacitors. So I'm going to say that the voltage on a capacitor is going to be its charge divided by its capacitance. So that'll tell me that V1 equals Q1 divided by C1. So I'm going to take, 259.875 and divide by C1, 16.5. This is in micros, and this is also in micros. So when you solve this, you're going to get 15.75 plain old volts. I'm going to play the same game for V2. V2 is going to equal Q2 divided by C2. So Q2 is the same as Q1, 259.875, but it has a different capacitance, 49.875. 16.5. Again, both of these are in micros, so when I run this through the calculator, you should get around 5.25 volts. Okay, so that's part C. I found the voltage across both those capacitors. Okay. Last up here, we have how much electrostatic potential energy is stored in C1 and C2, and what's the total energy stored in the system. Okay, so we're looking at energy on a capacitor. I'm going to remind you, I see students, I don't know, confuse the prior unit with this unit. They think of like, it is potential energy. And so sometimes when they see that potential energy, they just want to do a QV. But remember, this is for a charge in an electric field. And this isn't appropriate in this situation. What we have is a potential for in a capacitor. And that charge is on those plates. Not a charge in an electric field, but the charge on those plates are contributing to that potential energy. So this is a 1/2 CV squared, 1/2 QV, or Q squared over 2C. Okay, so which version do we like better? It seems like we have the C's and the V's and the Q's for all of the capacitors. U1, I'm going to do, what's the easiest one here? I always go back to what numbers I were given in the problem. I was given C. Q is easy as well. So I'm going to do Q1 squared over 2C1. U2 is going to be Q2 squared over 2C2. And I can plug that stuff in. What do we get? 259.875 squared divided by 2 times 16.5. You can run that through your calculator. 259.875 squared divided by 2 times 49.5. And I do believe if you don't convert, you're going to get this in microjoules. From what I can tell, you would want to convert to actual joules or whatever the question's asking you here. I didn't solve numbers here, but that's how I would solve it, is just plug those numbers through my calculator. And I'm going to note for any circuit with any, it doesn't matter if it's series or parallel, if I want to find the total energy here, I'm just going to take U1 and add on U2. And then I can be done with that problem. Okay. Parallel one, we can do this pretty quick. What's the equivalent capacitance? Well, we know for parallel, they add together. They just add together. So Q equivalent is going to be 5.5 plus 22, and that is 27.5 microfarads. Done. Pretty easy. What's the charge on each capacitor? Oh, no. Charge, we have to add together, and those are both unknowns. Because Q equivalent, this equation won't help because we have two unknowns. I'm going to go back to what I just said that always works, is Q equals CV. For this problem, both of those capacitors are connected in parallel with that battery. So when I look at these two branches are going to have the same voltage as the battery. So if I want to find Q1, I'll take C1 and multiply by the voltage of the battery. If I want to find Q2, I'm going to take C2 and multiply by the voltage of the battery. Okay, so again, if these relationships aren't working for you, remember to use the Q equals CV relationship that works for all capacitors. Okay, so C1 is 5.5 and the battery is 3, so we're going to get 16.5, and that'll be microcoulombs there. And then also this will be 22 times 3, and you can guess that's 66 microcoulombs. If we wanted to find the total charge on that equivalent capacitor, if I redrew this to an equivalent capacitor, there's an equivalent capacitor, C equivalent. I would just add those two charges together, and then that would equal Q equivalent, and then I could find that. Part C, what's the drop of potential across each capacitor? Oh no, we already did this, didn't we? Both of those capacitors, because they're in parallel, have the voltage of the battery. So I'm going to say both of them are 3 volts. I already did use that information in part B in order to solve part B. Part D here, how much electrostatic potential energy is stored in C1 and in C2? So we want to find U1 and we want to find U2. We have the charge on both of them. We have the voltage on both of them. We have the capacitance. I think if I am using my most accurate numbers, I always go back to what I was given in the problem. I was given capacitance and voltage, so I would probably do 1/2 CV squared. So I'll go 1/2 C1 V1 squared, 1/2 C2 V2 squared. So 1/2 times 5.5 micros times the voltage, which is 3, and then square it. Remember, this is micros, so when I solve this, I'm going to get a micro. You might want to just convert it to joules. If you convert it to joules, I'm going to keep it in micros, actually. This will be 24.75 microjoules. 1/2 times 22 times 3 squared. So that'll be 99 microjoules. Again, if you wanted to find the total energy stored in the system, you would just add them together. Not too bad. Okay. So returning to this problem from earlier, remember we did this first part, Q equivalent or C equivalent for this circuit. 26.5489 microfarads. That was fun and easy, all right? Then it started asking some more complicated questions, and we had a complicated network, and so I reviewed series and parallel, just in series, just in parallel, what's going on with stuff there. Here they want total charge stored in the system, total charge. So that is Q equivalent. What is Q equivalent? Q equivalent. The easiest way to get at Q equivalent, and remember when I simplified this, if I draw this, basically I've simplified it down to one equivalent capacitor. There's the battery, there's point B, and I have an equivalent capacitor. So instead of trying to find like Q1, Q2, Q3, all of that up there, what we're going to do is we're just going to use all of the circuit, this simplified final circuit, this redrawn, right? I bug you about redrawing it, but just redraw it. And notice that Q equivalent, I'm just going to note, is going to be C equivalent times the voltage across that equivalent capacitor, which is actually the voltage across the battery here. So I can multiply those things together, 26.5489 micros, remember that's micros, and then my voltage here is 3 volts. So Q equivalent for this circuit is going to be 79.6466 microcoulombs. We got a microcoulombs there, okay? I changed this. We're going to find the charge stored on C4. You can see C4 there. Okay. It's not buried. It's not like C5 or C6 buried in the circuit down there, but it is not as straightforward as just one equation. This is not a plug and chug. So what I'm going to do is kind of dissect my circuit. This is the equivalent circuit, but I'm going to kind of draw a simplified one. C1 is here, and then when I locate C4, C4 is in parallel with this equivalent capacitor of C2, 3, 5, 6 over here. Okay, you remember doing that earlier in this lesson. There's B and there's A. So it seems like if I wanted to find Q4, right? The charge stored on C4, Q4, right there. I would take C4 and multiply by V4. That would be a good idea, right? When I look at this circuit, there is going to be a voltage drop from this point to this point, which is V4. That'd be the same as, because they're in parallel, V2, 3, 5, 6. So if I knew the voltage drop from this point midway to point B, I would be able to find Q4. How do I find that? Oh my gosh. Well, let's see. V4, what I'm going to remember is V4 is in series with C1, which is a V1, right? So for this part of the circuit, there's a V1. And when I add those together, because they're in series, voltage from the battery has to equal V1 plus V4. So if I found V1, I could find V4, right? If I just do some subtraction, V4 equals V from the battery minus V1. You may be asking, like, Sarah, how do you know to find V1? How do you know how to find V1? Why is that? I'm going to remind you that we have this equivalent charge. And when we're looking at series, I don't have the little summary slide up there, but for series, Q equivalent equals Q1 equals Q2, but in this situation, we'd have like, Q2, 3, 4, 5, 6, all of that charge, all of those capacitors added together. So I have Q1 because I have the equivalent charge. So I'm going to note that V1 equals Q1, or Q equivalent, divided by C1. So I can find V1. So Q equivalent is 79.6466 micros. C1 is 49 micros. And when you run this through your calculator, what I'm seeing in my notes is you get 1.625 volts. Not too bad when you run that through. Yeah, that seems right. Now that we have that, we can find V4. V4, I'm going to note, is 3 volts from the battery minus that 1.625 volts that I just found. And so V4 is 1.375 volts. Okay, now that I have that, I can take it and plug it over into my equation I set up earlier. C4 again is 30.5 microfarads, and then my voltage is 1.375 volts. And so the charge across C4 is going to be a nice 41.9 microcoulombs. And that's how I would do that. Note again, my tip, redraw this circuit. I needed to go back to some earlier version to dissect, to isolate down to C4 and relate those voltages and charges together to solve for that. So let's do this last part, the total energy stored in the system. Well, you've seen in the past two, I could find the energy stored in each capacitor and then add them all together. A convenient thing to do here is just going to do the equivalent for the whole circuit. C equivalent V squared, whatever that voltage on the battery is. I would just do it that way. 1/2 26.5489 micros, and the voltage on the battery is 3 squared, and that will give you a total energy of 119.47 microjoules on that circuit. Okay. So these can be this more complicated capacitor networks. Take your time on them. I know people want to jump into them and try to make it simpler than what it really is. Redraw your circuits and take your time on it dissect it through, and it takes some practice, but I'm confident that you'll figure it out. And just a summary slide here. Recall Q equals CV. You can take a screenshot or copy this into your notes so that you have it when you are solving problems.